Okay, so we look at these limits here, 1 to infinity, 0 to 0, and infinity to the 0 power limits. All of these are centered around this algebraic fact that if you take the exponential function and raise it to the logarithm function, that those two things cancel each other out. Okay. What we're actually going to end up doing is taking our limits, right, and rephrasing them so that they involve an exponential and a log. The log limits will let us transform these, the log of this stuff, of any one of these three, will transform these into a 0 times infinity limit, which we can then manage. Okay, every one will transform into a 0 times infinity limit in some way. Okay, so that's what we're going to be leveraging, and I'll show you how it works by looking at a function that we would be kind of hard-pressed to be able to think about without this logarithmic approach. So let's consider the limit as x approaches 0 from the positive direction of the function x to the x. This, of course, is a 0 to the 0 limit in this example. Okay. So the key idea is that if you take e to the ln of something, it's equal to the original thing. So if I take e and raise it to the ln of x to the x, right, that is the same as x to the x, because the e and the ln cancel out. So what I look at, instead of trying to look at this limit, what I do is look at the ln of that thing. So we consider that limit first. So we step away from the original problem for the moment. We say, hey, let's consider the limit as x approaches 0 from the positive direction of the ln of the thing we're trying to take the limit of. Okay. So what we're going to do is work this out. Once we have an answer for that, right, then we'll go back and say our limit, this thing, is equal to e to that, whatever that is. So we just raise e to whatever this limit is to get the original limit. Okay. So by looking at the ln, we're able to invoke properties of logarithms, which allow us to bring that exponent out front and have the limit of x ln of x. Have the limit of x ln of x. Okay. And this, of course, is quite simply a 0 times infinity limit. Right? This is a 0 times infinity limit, as again, all three of these will be when you apply a logarithm to them. They will turn into 0 times infinity or infinity times 0 limits. Remember, the infinity times 0 or 0 times infinity, we can compute those by taking one of these two things over the reciprocal of the other. Okay. Now, you are free to choose, but let's be quite frank, we definitely would prefer ln over the reciprocal of the other, compared to doing x over the reciprocal of the ln. We can do that. Darn it, 1 over ln of x is going to require us to do the derivative with the quotient rule. That's going to be kind of yuck. Whereas this way, the 1 over x in the bottom is much easier to differentiate. Okay, so we make that step, and what that does is that transforms this now into an infinity. Ln is going to go to infinity. 1 over x, as x goes to 0, is going to go to infinity. So we've now transformed our problem into an infinity over infinity limit, which we can now invoke and simplify with L'Hopital's rule by applying the derivative applying the derivative. Okay. So this is going to be limit as x goes to 0 from the positive direction of the derivative of ln, which is 1 over x, times the derivative of 1 over x. It should be negative x to the minus second. And then we just have to simplify this. We have 1 over x divided by negative 1 over x squared. Which would be 1 over x times the negative of x squared, which would be negative x. So that fraction is just going to simplify to be negative x, and now we have limit as x approaches 0 for the positive direction of just negative x. And of course, we can just let x be 0. Okay. So at this point, we've worked out the limit involving this piece. Okay, involving this piece. ln of that stuff. To actually figure out the original limit now, we go back and say the original function x to the x is e to the ln of x to the x. Since we now know what ln of x to the x approaches, we know that the whole thing is going to approach e to whatever that is. So, in other words, the closing step here is to go back to my original limit and say, hey, that's the same as e to whatever the other limit is. In this case, it's e to the 0, which is 1. And so now we've worked out our first indeterminate form that involved an exponential limit. Okay. It was a 0 to the 0 limit, which in this case turned out to be 1. So it turns out the x to the x function, as x goes to 0, actually approaches 1. That's actually pretty cool. What's x to the x look like? Well, here you go. First of all, x to the x does not exist, of course, for negative numbers. Makes sense, right? And so there he is. And you can see it doesn't actually have a point, although my graph, for some reason, my graphing device, for some reason, actually plots the point there, even though 0 to the 0 is not 1. It's coming up with some bug in its programming. It's coming up with some bug in its programming, so it's not working properly. It should not actually have that as a point on the graph. That should be an open circle there, because 0 to the 0 is not defined. But we can see there from the graph it does at least agree with what we've been finding.